Hi, everyone. So I've talked about this event before, so it might look familiar to a few of you. So this is one event, one complicated event that is helping us understand the tools that we need to get accurate mass measurements, especially for M dwarfs in the disk. So MOA-2010-BLG-328 is a binary lens, binary source event with higher order effects of parallax, orbital motion, and xallarap. The initial study was carried out by Furusawa et al., and they found a degenerate light curve, which we hope to solve with high angular resolution data from Keck and HST, which we got in 2018, 8 years after the peak of the microlensing event. So we followed the usual procedure where we tried to resolve the source in the lens, measure the amplitude and direction of the proper motion and the individual luminosities. We achieved this with the Keck K-band data, but we were not able to in HST's VNI, which is unfortunate. But at the time, the separation was only 35 milliarcseconds, and the lens was too faint to be in these passbands to be detected in the PSF wings of the source star. And I say this is unfortunate because with the K-band data and proper motion measurement alone, the degeneracy continues. And this is highlighted on the mass distance diagram, where the two relations, one due to the Einstein ring radius and one due to the lens's luminosity, they don't appear to intersect at any one particular point. So we remodeled the light curve using the follow-up data as constraints, and we saw that without being able to constrain the parallax, we get two possible solutions. And we investigated these by looking at the probability distribution of parallax values. We separated them into large and small and looked at them separately, with large and small being determined by that criteria there. And we saw that the large parallax values were responsible for a lower mass lens that is closer to us, whereas the smaller parallax values were responsible for a higher mass lens further away from us. And this ambiguity is common for M dwarfs in the disk, where early type M dwarfs that are further away from us can appear to look like late type M dwarfs that are closer to us, if you don't have the right color information, especially in shorter wavelengths. So we're interested in seeing how additional data could help us constrain the physical parameters of these systems, and in particular, which shorter wavelengths would work best, and of course, how does this translate to Roman passbands? Thank you.
So just to be clear, for this event, you had to include xallarap, parallax, and orbital motion?
Yes.
Okay.
Also, the lens aim source, right?
Yeah, the source was.
Oh, so it's not just a pure xallarap, it's binary source as well. Okay. It's impressive.
The model takes a month to run.
Because my code is binary lens code in addition.
Any questions? Okay. Yeah.
Also here, if the source is a 16 million, there is no problem. That's the topic the other last.
I don't know, but it would be